In this video, we will see 3 examples of transforming non-exact differential equations into exact equations by using integrating factors. Example 1. This equation is not linear because you have the y squared and the y times y prime. And this equation is not separable either. So we'll check whether or not it's exact. As usual, we're going to denote the 2 coefficients as m and n, and we need to find the y derivative of m and x derivative of the n. And we understand when we do the partial derivatives, we're going to treat the variable of differentiation as the variable, and all the other variables, we just treat them as constants. So that's why here, the 3x squared will give you 0 if you do the derivative with respect to y. So clearly, we can see the 2 partial derivatives, they are not identical. That means this equation is not exact. Well, because we don't have any other approach to solve it, so we'll try to convert this equation into an exact one by using the integrating factor. In particular, we're going to multiply a function mu to the equation, and we want this equivalent equation to be exact. That means if we denote the new coefficients by m hat and n hat, then we must have the y derivative of the m hat and the x derivative of the n hat identical. So this becomes a condition for the mu function. So we just need to carry out the derivatives of the 2 functions here with respect to the y and x respectively. And because you have products here, so we have to apply the product rule. In particular, for the left-hand side, we apply the product rule with respect to the y derivative. And for the right-hand side, you do the product rule for the x derivative. And now we can use the conditions we get. We have the partial derivatives already here, right? We can plug them into the equation here, and we get a condition for the mu. Now let's copy this equation. And if you take a look at this equation, you notice that we have both x derivative and y derivative of mu involved. That means this equation is a partial differential equation. And we know usually it's more difficult to solve a PDE than solving an ODE. So it seems like we got a more difficult problem to solve. But on the other hand, we understand this mu function is actually under our control because we multiply something to the original equation, right? So what you want to multiply to the equation is kind of under your control, right? So instead of making mu as a function of both x and y, we can assume mu depends only on one variable. Either it's a function of x or it could be a function of y, okay? Which one works? Well, we will just try, okay? For example, let's just try to consider mu as a function of x. In this case, we understand the y derivative of the function is going to be 0 because the mu here has nothing to do with y, right? So if you make change in terms of y, this function won't change. So that's why the y derivative here is 0. Therefore, we know the 0 times whatever is going to be still 0, right? So this term is going to be canceled, okay? And now you got just a mu and its x derivative involved in this equation. We combine the mu terms, and you'll get, for example, here we move this term to the other side. You're going to get a minus twice of x, and then minus tends to plus. You're going to get 4 times the y, right? So you can say here, -2, right? So basically, we factor the -2 out, and we will say left-hand side is going to be negative twice of x minus 2y times mu. And then for this term, we can factor the x out. And then we also get a factor of x minus 2y. So understand this thing can be canceled, right? And we end up with the equation of mu and x. So this is consistent with our assumption here. We assume mu is a function of x, so that its derivative is only going to be related to x, as we observed here, okay? So now we can solve this equation. Well, this turns out to be a separable equation, okay? We can separate the mu and the x, and then we integrate both sides. You will see this will give you the natural log of mu, and this part, you're gonna get negative twice of natural log of x. We apply the properties of log, bring the coefficient into the log. It will become the exponent, right? And then we notice that the mu is in the position of x to the negative 2. So we can pick our mu as x to the negative second power. And then we just copy the equation 1, okay? This is the equivalent equation to the original one, right? And we said we want this one to be exact, right? So now we just carry out, you just plug the mu expression into the two coefficients. You carry out the coefficients, okay? You're going to see the m hat and the n hat. And if you check the y derivative for m hat, your get is going to be twice of x to the negative second power times y, which is the same as the x derivative of the n hat. So means this equation is indeed exact. Now we understand there will be a potential function psi such that its x derivative is going to be the m hat and its y derivative is going to be the n hat. And we can get the psi from the antiderivatives of m and n with respect to x and y respectively, okay? So in particular, you can just integrate the m with respect to x. And we know the m here is just an expression of powers of x, right? And we can use the power rule and get the antiderivative. It's quite straightforward. Similarly, from the condition for n, you can do the antiderivative with respect to y. It's also a power of y, okay, which is easy to integrate. So we understand for exact equations, when you do the integrations with respect to x and y here, sometimes we end up with some expressions not really consistent, okay? That's because the constant is not really a constant number, okay? When you talk about the integration with respect to x, you are considering y as a constant, okay? So that's why you don't see this y term, okay? Basically, the y is contained in here, okay? Similarly, when we do the integration with respect to y, we consider x as a constant. So that's why we do not see the 3x and minus 4 times of x to the negative first power in the second expression, because they are contained in here, okay? So now we understand basically these two actually, they are consistent, okay? We don't have any conflict, although they look different. And we can just collect all the terms in these two expressions to get our psi function. And we know the general solution to this equation is going to be the psi is equal to a constant, which will be just this equation, okay? It's defined implicitly by this equation. Well, for this problem, because we have an initial condition, so we need to apply it to determine the psi here. In particular, the initial condition is y of 1 is equal to 2. So that means when x is equal to 1, your y is equal to 2. So we can just plug these two numbers into the places of x and y's. And then you get an equation for psi. Easily, you can get your psi is going to be -3. And then finally, we simply replace the psi here by the -3. And then we can get a particular solution for the initial value problem. So in this example, we solved a nonlinear, non-separable, non-exact equation, right? By using integrating factor. Okay, now let's say example 2. So again, this one is not linear. And it's not separable. Okay. So we will first of all check whether or not this equation is exact. As usual, we're going to define the coefficients as m and n. We check out the y derivative of m and the x derivative for n. And apparently, these two partial derivatives, they are not identical. That means this equation is not exact. Well, here, because we cannot convert it into a linear equation or a separable equation, so we'll just try to convert this to an exact equation by using an integrating factor. Namely, we're going to multiply a mu function to the original equation, okay? And this is equivalent to the original, right? Yeah, so this equation 2 is equivalent to the original equation. And we want this one to be exact. That means the new coefficients, if we denote them once again by m hat and n hat, these two coefficients will satisfy the condition for exact equation. So here, once again, we have to use a product rule to carry out the two derivatives, okay? Because here we have product of the original coefficient and the integrating factor, right? Okay, now by using the product rule, you will say left-hand side, we had to do the derivative with respect to y, right? And the right-hand side, we had to do the derivative with respect to x, right? Okay, and then we realize for some part, like the coefficients derivatives, right? We already got them in the first part of the solution, right? When we check the original equation, we already got these two, right? So we can plug them into this equation and we get a condition for the mu. Okay, once again, we're going to focus on this one. And this time, again, we're going to get a PDE for the mu. But we already know from the first example that we can just think about mu as either a function of x or a function of y, so that you do not have to solve a PDE here, right? So we'll just try the idea of mu as a function of x. So in this case, we understand the y derivative for this function is going to be 0. And the term with the mu sub y is going to be 0. You can end with the equation with only mu and mu x. We combine the mu terms. We'll end with the equation which is not only an equation of x, but also you have y involved, right? So that means your mu and its derivative depends not only on x, but also on y, which is a contradiction to our assumption here, okay? But just think about if you have a function depends only on x, then when you do the integrations, I mean, when you do the derivatives, you still get only x, right? So anyway, you're not going to get some y involved, right? Yeah. So that means the assumption we made over here is not a good one, okay? Well, in this case, we'll just try the mu as a function of y. Well, in this case, we understand the x derivative of the mu is going to be 0. And in the equation, original equation here, okay, you understand the term with the mu sub x is going to be 0 as well. And you're going to get the equation of mu and the mu sub y. We combine the mu terms. You can see the 2y, you subtract from both sides. You're going to get x plus 2y, right? And then plus 2, this many mu. And for the mu sub y term, we factor the common factor y here. We also get the factor of x plus 2y plus 2. And then we know this common factor can be canceled. Just divide both sides by this. And then we end up with the equation of mu and y. Okay, so that means your mu here depends on y, which is what we assumed, right? So we can go ahead and solve this. We know this, again, is a separable equation for mu, right? So we separate the mu and y, we integrate both sides, we're going to get the natural log of mu is going to be negative natural log of y, and we understand the negative sign, which is a coefficient, can be put inside of the log, right, as an exponent here, right? You're going to get y to the negative 1. So therefore, your mu is in the position of y to the negative first power, right? And that's why we can pick our mu as y to the negative first. Okay, now we just copy our equation to the equivalent one to the given equation, right? And we substitute the y to the negative first power into the equation. And then we get this new equation is going to be an exact equation. Actually, it's pretty easy to check, right? So if you do the y derivative for the m hat here, you're going to get just the 2, right? Because x here is a constant, right? Its derivative is going to be 0. And the 2 is going to give you a 0. So you're going to get just the 2. And for the x derivative of the n, you're also going to get a 2, okay? Because this time, the y is treated as a constant. So that's why it's exact. And therefore, there's a potential function satisfies the 2 conditions, right? Namely, you get the size of x is equal to m and the size of y is equal to n. And we can just do the integration of m and n with respect to x and y respectively, okay? So in particular, for the first one, you can say here, it's a polynomial of x, right? So its antiderivative is very much straightforward. Here, the y is treated as a constant, right? And the constant term here could be a function of y. And similarly, you will just integrate the n hat with respect to y. And this is also a power of y, right? So its antiderivative is also quite straightforward, okay? And the constant term here, it could be a function of x, okay? So that explains why we won't say the half of x squared term and the 2x term in the second expression, okay? And it also explains, this guy explains why we don't say the 5 times of natural log of y in the first expression, okay? Okay, finally, we just collect all the terms and also recall that the y in this example is greater than 0, right? So our psi function can be just denoted like this. And then we know the solution to the original equation is going to be also the solution to the equivalent equation, right? Which is going to be the psi function equal to c, right? And finally, you're going to say the solution to the equation is going to be implicitly defined by this equation. Example 3. Well, for this example, actually, it is linear. Okay, so you can see the dy here, right? dy dx, and you have only one y term here, right? Yeah, but we still want to try the approach we did in the first 2 examples here. Okay. So first of all, we're going to denote the coefficients as m and n. And we want to check the y derivative of m and the x derivative of n. And here, because we're going to treat the x as constants when we do derivative with respect to y, that's why you're going to see the zeros, right? So the only thing not 0 is going to be just the first term will give you an x, okay? And the second function's derivative is pretty straightforward, right? Well, clearly, these two are not identical, and we know this equation is not exact. And now we just want to multiply the equation by an integrating factor mu. and we get a equivalent equation number 3 here. We want this one to be exact. And to be an exact equation, we understand the new coefficients. We can call them m hat and n hat, okay? The new coefficients. They need to satisfy the condition. So basically, we just need to take the derivatives, okay? The corresponding derivatives. Because you have products, right? For both of the m hat and n hat, we're going to use a product rule. So for the left-hand side, you do the y derivatives. Right-hand side, you do the x derivatives. And for the coefficients, the old coefficients, you already got the derivatives, right? You already got the derivatives. So we plug them in. So we can get like a condition for the integrating factor mu again. And this condition, once again, is going to be a PDE, right? You have the mu sub x and the mu sub y. And we can use the same idea. So we can assume this function, for example, as a function of x. And it follows that the y derivative is going to be 0. So that this term, a multiple of mu sub y, is going to be 0, right? And we get a pretty simple equation of mu and mu sub x, right? And we combine the two mu terms. You will get, this will be the equation, okay? You can simplify further, right? You have the x can be simplified. And then we know we get a separable equation for the mu. So then we can just separate the mu and x. We integrate both sides. And then we can get the natural log of mu is going to be natural log of x to the negative first power plus a constant, okay? So here, the mu is in the position of x to the negative first. So we can simply pick our mu as x to negative first. And now we just rewrite our equation 3 here. And we plug the expression into this equation, okay? You will say that will be the equation equivalent to the original one after you multiplied the integrating factor to it. And pretty easily you can check this equation is going to be exact, okay? Because if you do the y derivative for m, you can say this is only term with y, right? So its derivative is going to be 1. These two terms, although they look pretty complicated, but their derivatives with respect to y will be just zeros. And for n sub x, it's clearly 1, right? So we know this equation is exact. Okay, now for an exact equation, we understand there's a potential function psi such that the psi sub x is m hat, and the psi sub y is going to be the n hat, right? So we need to integrate the m hat with respect to x to get the psi. So here you can say, well, for the 3 terms here, the first term is actually a constant, right? Because you are talking about the antiderivative with respect to x. So y is treated as constant. And for the next 2 terms, we can try to use substitution. Okay, actually substitution works. Okay, in particular, for the second term, you can see I did the work over here. Okay, we can just figure out, well, we have 2 terms right here. And the log x is actually a troublemaker for this problem, right? So we're going to take the new variable u as log x. And then we know the du is going to be x to the negative first power dx. That means these 2 parts will give you just the du, right? So we know the original integration of x will become an integration of u as, you know, the integration of u du, right? Its antiderivative is pretty straightforward. And then you plug the definition of u into the expression. So that's why we will get the second term's antiderivative is just twice of natural log of x squared. Okay. Now, for the third term, we also need to do substitution. Okay. So for this case, we understand the troublemaker here is going to be x squared, right? Yeah, sine x squared, x squared will be the troublemaker. So we will just let this part as the new variable u. And then we know that du is going to be twice of x dx, so that your x dx will be half of du. Therefore, the original integration of x with respect to x here, okay, can be written as an integration of a u function, right? So you're going to get sine u and you get half of du. And its antiderivative is going to be just a negative half of cosine u, which is negative half of cosine x squared. So that's why you see the last term's antiderivative is going to be this. Okay. Of course, the first one, because the y is a constant, its antiderivative is quite straightforward, right? Well, that's the precise expression after we integrate the m with respect to x. And now we're going to do the same thing for the n here. Because n's expression is pretty simple, right? It's just the x, right? Which here is a constant. We don't do the antiderivatives with respect to y here, right? So your get is integration, it's simply x times y and a constant here, okay? Okay, now we can just collect the terms in these two expressions, right? We understand we do not say the long expression here for x. It's just because they are all contained in here, right? In the constant for the second expression, okay? So we can set our psi to be, the three terms here, okay? So xy minus twice of natural log of x squared minus half of cosine x squared, and then plus a constant c. And then we understand the solution to the equation is going to be the psi function equal to c, okay? Which is implicitly defined by this equation. Okay. Well, we just mentioned at the beginning, this equation actually is also linear, right? So you can solve it by using the standard approach for a linear equation. Okay. But the substitution, for example, we did for the two terms will be also needed if you use that approach. Okay. So the essential part of calculation is still going to be needed. Okay, you need to carry out the essential part. It's not going to save you the work. Okay, yeah. Okay, so that's all for this video, and thank you for watching.